Hello students, welcome back. Previously we went through a constraint optimization problem, which is typically structured this way, and an example problem here associated to this visualization. How do you minimize this area right here? That was the problem, remember? And the solution went like this. The structure here, constraint condition is volume of 32,000, which is x squared times y. Look at the picture, x squared times y, base area times height. And the constraint condition, x squared plus 4xy. So we have this structure, constraint condition and objective function. By the way, objective function is the area here. X squared is the base area, and 4 times the area of the rectangle xy. That's how I got this. Now, solving for one variable and plugging into the other, solving for y and plugging in, we get a function of one variable only. And then from here, take the derivative and set it equal to 0. You can get x equal to 40. Plug it back in, you get y is 20, so we get the dimension. X is 40, y is 20. So the desired dimension is 40 by 40 by 20. Let's go back to the visualization. Down here, 40 by 40, and this height is 20. So this one is a bit too flat as a matter of fact, because this height has to be half as this width. Okay, that was a quick review, and let's resume. The second half of the problem. An open top box with a square bottom must have a volume of 32 cubic centimeters, same as before. Suppose further that the material for the bottom is twice as expensive as the material for the side. So in this situation, we have the same volume here, consequently the same constraint condition, but the objective function will differ this time. Let's copy and paste this thing, and then paste it here, and then let's check that with this picture. Constraint condition, the volume is bottom area times height is 32,000. Objective function, previously the area, and then bottom area x squared plus 4xy, because there are 4 sides and each has the area of x times y. Well, that was the objective function for the previous problem. This time things are a little bit different. Suppose further the material for the bottom is twice as expensive. So for the bottom area, I have to multiply by 2. And let's call it not just the area, but the cost function. Do you see how this 2 is coming into play? The problem said twice as expensive. If this had been 3 times as expensive, you'll have to multiply by 3. So that's the setup. Previously, we didn't have this 2. It was just x squared. Now we have this 2 because of this adjustment. Alright? Now we don't need this picture anymore. Let's go ahead and solve this. I don't need this one anymore either. So from the constraint condition, so for y and plug into the cost, the other function, objective function. So v is x squared y, that's 32,000, excuse me. So y is 32,000 over x squared, which is 32,000 negative second power, and put that into the objective function. and y is this one right here. Let's put some space in between. And this simplifies into 2x squared plus 4 times 32, 64, and then negative first power only. And I don't have y anymore, so I can call it c of x. So we are ready. We can take the derivative and set it equal to 0. 4 times 32 is not 64, it's 128, isn't it? Okay, alright, sorry about math mistake. Okay, alright, now this is correct, and let's go ahead. Let's take the derivative and set it equal to 0. 4x minus 128, 0, 0, 0, x to the negative second power, and set it equal to 0. Okay, alright. Divide each by 4. X minus and divide by 4. Multiply by x squared, so we get x to the third power, and this is going to be gone. And that'll give me x to the third power is 3,200, no, 32,000. Therefore, x is cubing root of this. And for this, I'm going to need a calculator. Let's see. What is this quantity? I can go to calculator, but I have calculator with me, so let's go ahead and do this computation. 31.748 approximately speaking. So that is my x value. How about y? Well, let's put it into this. So 32,000 divided by this quantity, 31.748. Oh, I forgot to square that. Sorry about that. Okay, alright. That makes a bit more sense. By some strange coincidence, we got the same values before. Consequently, what's the configuration? You're going to get a cube. Base is a square, x by x, and height is also x, so not like this. It's a lot taller. You're going to get some cube. The optimal dimension is about 31.75 by just 748 by 31.748 by 31.748. And in this case, the minimal cost I have to plug that into this cost function. Yeah, that's the function value. And I have to plug in this value in, right? Doesn't work very well. Okay, that's the quantity. And then I'm plugging in this. No, that's not the right expression. This is the right expression. Okay, that's cost function. That's the right expression. And then there I'm plugging in this. And then this. Okay, 6047 something. And then, the problem says just the bottom is twice as expensive. Not the precise monetary value, the conversion factor for dollar amount. So I guess this computation or this expression is actually meaningless. I should not have emphasized this. Yeah, I just realized it now that I will kind of write the answer. So let's stop here. Let's look at the answer key. Same computation, we get this 2 because the bottom material is twice as expensive. And then same, or the same, or the same, and then we have cubic configuration. Okay, we completed this example, and finally we have one more example here. This one I'll leave to students. It's gonna be really hard, but you can do that. Kind of like this. We want to maximize this area, and you have to follow this curve, and there's the equation. That's the constraint condition. As for the objective function, let's see. X is the horizontal distance from the origin. So in order to get the entire width, I have to double it. 2x. Same for y. I have to double it in order to get here negative y to positive y. So the objective function is 2x times 2y, 4xy. So there's the constraint condition, and here's the objective function. Solve for one variable, plug into the other, and then run your calculation. If you do it right in the end, you're gonna get this. X is a square root of 2, and y is b square root of 2. Okay, the detail is left to the students. It's gonna be really hard.